Everyone, my name is Luganzi Matthias Joseph, and I'm working in Nursery Catherine. This is Group 27. The title is Reinforced Generative Adversarial Contrastive Learning for Defective Tire Defect Detection in Age Installation. To give a brief description and background of the study, tires, one of tire defects are one of the major cause of accidents on the roads. Yeah, and I'm looking on the factors that cause this is overinflation, deflation, wear and tear, and poor rim alignment. Um, the traditional methods that are being used for inspection are visual inspection and edge inspection, physical inspection, and alignment inspection, which are not as efficient as they should be because as people are still producing defective tires and actually running on bad roads. But coming up with the effective methods such as generative adversarial contrastive learning, computer vision, and image processing, where we have convolution neural networks and investigation, we can be able to have models that can distinguish between good and effective tires. And the related works, X-ray images are one of the major models that are being used in factories to check tires, whereby tires are run through an X-ray machine and 2D output is given, and then it's inspected for defects. Then simple machine learning models such as support vector machines are also being used, but these are less efficient and effective and accurate, which makes it still a great problem. Then to move on to the domain problem, the basis of this study, and to look at the traditional methods, see that they are still affected by accuracy and then real-time processing. And since these are not able to distinguish between good and effective tires, due to the high resolution size of the images, that intricate details that are on the make up the structure of the tire, it being hard and complex, having different texture patterns, it's hard for a model to distinguish between good and effective. So the computational problem statement, high resolution images which require higher storage, high processing power, feature extraction, and that all makes it hard to make an efficient model. Then real-time processing, models must balance between complexity, speed, and provide real-time defect detection, high resolution images. Then large-scale images, which makes it hard to handle large datasets. Meaning you have to employ data augmentation, hyperparameter tuning, and parallel processing. In such questions, here we're looking at how we can optimize models for real-time processing while maintaining the high accuracy, and also looking at how we can use our computational strategies to be implement handle large scale datasets and high resolution images. Then also generative adversarial neural networks to optimize generative high quality synthetic tiles. Yeah, we addressed some of those using our objectives and to apply contrastive learning for feature separation, to effectively distinguish between defective and good tires, and also apply net distillation for model efficiency and ensuring better generalization while minimizing computation overhead. The research contributions were able to develop hybrid models that incorporated contrastive learning, distillation, and reinforced learning, which improved image classification, and also able to come up with contrastive learning techniques that effectively separated features. And this enables to improve quality image classification, and then legislation to come up with lightweight models. The methodology, looking at the methodology, we look at the architecture, by which begins with obtaining the dataset for the images, then performing an EDA to understand the distribution of the image of the tiles, and then preparing and processing data, feature extraction, and then contrastive learning, model training and evaluation, and then deployment. The dataset was obtained from Mendeley, and it comprised of about 1,000 images of high quality pixels. And then we did an EDA to understand the distribution, light intensity, and also the features correlation between the images. So we are able to develop about 10 models, and one of the models was reinforced teacher supervised learning model, whereby the model was using a reinforced learning technique to teach the teacher model and then transfers the knowledge to a lightweight student SKNN model. And these were results that look a bit accurate of about 97 accuracy and also 94 yeah, to add on, we did other models like mobile VNet, we did models like DC GAN, VDG, and in baseline CNN. But talk about the VSNet model. The VSNet model was able to create a pre-trained model that was improving with the number of training, whereby if you have a large number of epoch, you're able to have a better model. And then we did a SGSM attack on the images after like training the model to see whether it could still predict the output. So the image shows the results before the attack, and the other side you have images after the attack, and the model could still distinguish between good and effective tires. Thank you. My colleague will take on from here.
Hi there, my name is Nasali Catherine, and I'm going to be taking you through explainable AI. When we trained the models, we realized that we weren't sure what the model was basing on when making predictions. So with this, we decided to use Salience maps, LAME, and counterfactual to identify how this model came up with these predictions. So with Salience maps, we used it because it computes the gradients of the output with respect to the input features. And you see the highlighted areas on this tire that you see here. These are the features that the model used when making this prediction. As for LAME perturbs the input, this image that you see here, and then observes the output of the model that we have. So this is the mobile ViTruNet that was being used. We also used counterfactual, where counterfactual, like LAME does, it adds something to the image and then compares the results. And with this, we were able to know how the model was coming to the prediction and what features it deemed worthy. Now for here, in this image, you realize it used light. We performed explainable AI to the teacher-student CNN model that used knowledge distillation. This was the worst performing model when it comes to all the models that use knowledge distillation, and wanted to know why. So after adding the techniques that we talked about before, LAME, counterfactual, and the saliency map, realized that the teacher and the student highlighted different areas. And when it comes to highlighting different areas, it means that this student did not learn from the teacher as we expected it to. It copied worse features from it, and that caused it to have poorer accuracies compared to the teacher itself. So with that, this is a table summarizing the results we had, and for all the models that are using knowledge distillation, the student is the one that we placed within the table. And as you can see, for the teacher student, they had an accuracy of 66. And as I said before, it did copy the features from the teacher as we expected it to. Mobile VNet had a 93 and the ResNet had a 94. So with this table as it says, we chose the mobile ViTruNet because it was a lightweight model, and compared to the ResNet models that we have here that has the highest accuracy, it had faster computing power compared to the other ones. We chose the mobile ViTruNet because it was a lightweight model. It was faster compared to all the other models that we had. The user uploads an image. Streamlit provided us with the user interface. We have the image. Once it's uploaded, it will be displayed, and then the prediction, the image will be sent to the model. The model will make the prediction, and then it will return the results to us. I'm going to show you the demonstration. Okay, so this is the demonstration for our project, and as you can see, we deployed our project on Hugging Face. When a person inputs the image, it will be displayed, and once it's displayed, the prediction button will appear at the bottom of the image. So once this button is pressed, it will return a result, and as you can see here, with this image that has been placed here, the tire was predicted as a good tire. So the reason as to why we used Hugging Face was because it gives us 4 instances for processors, and it gives us a lot of RAM for deploying our models. So with that, that is how our model works. So these are the IP assets for our work. We shall look at the combination of the reinforced GAN, the contrastive learning, and the knowledge distillation for training our model. We want to copyright our documentation, the trade secrets. We have the source code, the hyperparameter tuning strategies we used. Then for the novelty of our concept, we used a combination of GANs, contrastive learning, and knowledge distillation for tire defect detection. How is our model going to be useful? Yeah, so we intend to use this model. Sure. What were the limitations first while training these models? Handling large tire images led to memory bottlenecks and slow processing. So with that, we leveraged data augmentation to diversify the dataset and improve memory efficiency. Then we balanced the model complexity and the speed. Actually, we faced a problem with balancing the model complexity and the speed. So we employed model optimization techniques and used an efficient architecture to reduce the model size and speed, most especially in the mobile ViTuNet. What would be the next steps? We would like to integrate in IoT and use multi-defect detection classification on the tires. We would add computer vision to capture images of tires in real time using cameras. So we would like to acknowledge our supervisor, Mr. Galiwango Marvin, the Makere Unipod, for helping us with the pitching. And then we also would like to give special thanks to the Intellectual Property Management Office. Yes,